Alright, we're going to work with some exponential word problems now involving a special formula for growth and decay. And so I'm actually going to come back to this problem a little bit. Let's go down toward the bottom of the page and look at the special formula we're going to use. Here's how you say it out loud. A of t equals p times e to the kt. What's it all about? Well, I'd like you to grab an index card because you're going to use this formula quite a bit in your homework problems, and we want to be able to identify the parts of the formula, and there's just not quite enough room here. So I'm going to recopy the formula in the center of my index card. A of t equals p times e to the kt. Alright, so what's what in this equation? Well, we're usually going to be working with a problem about some amount growing or decreasing. It could be a population, it could be medication, it could be anything that grows or shrinks. So this p, let's start on this side of the equation. This p stands for the initial amount. The initial amount of something, either a beginning population, an initial amount of medicine, or the first week's box office, the original box office revenue, whatever. Now E, if you'll remember, is that special exponential number, which is about 2.718. Okay, so that's actually a number. And now T, let's do T next. This is time. So after a certain amount of time, what's happening to this population? So it could be time in minutes, years, seconds, whatever. Now K, this is something a little new. This is a rate, the rate that something is growing or decaying, and it's going to be a decimal. It's going to be a decimal form of a percent. So if something's increasing by 10%, we're going to use 0.10. Something's decreasing by 40%, we're going to use 0.40. So this is rate as a decimal. Okay? So make sure you get all those things identified. Now on the other side of the equation, A of t, the function of a certain amount of time, A stands for amount. So A of a certain time is the amount left, or the final amount, or the resulting amount. Let's write resulting amount. Resulting AMT, or amount. So if it's a population that's growing, we start with P amount and we multiply that by E to the rate times the time, and we get the final amount of the population. Alright, let's learn how to use this function now. Oh, by the way, a couple of additional things. As it mentions here, if K is positive, then it's something that's growing. If K is negative, then it's something that's decreasing or decaying. So let's put that note on our index card too. If K is positive, so K is greater than 0, then we've got growth. If K is less than 0, if it's negative, then we have what we call decay or decrease. Okay, so initial note, additional note. So let's see how we're going to use this formula. In this situation, we have in 2009 a world population of 6.8 billion. The exponential growth rate was 1.13% per year. We're going to find the exponential growth function. We're going to estimate the population of the world in 2012, which has already passed, and 2020, which is coming up. And then we're going to answer the question, when will the population be about 8 billion? So we need this function. We need this A of t equals p times e to the kt. And let's find out what we know and what we don't know so far. Alright, so we know the initial population. So we know P. Let's make a little list here. P equals 6.8 billion. You know what? We also know K. We know the rate, but here's the deal. We have to write it as a decimal form of a percent. So if it was just 1%, we would write 0.01, right? 1% is 1 out of 100, 1/100th. But since it's 1.13%, we need this 1/3 following. If you're not sure how to change a decimal, a percent to its decimal form, even though this is a decimal already, that's not what we mean. we need to divide this by 100. So if you take 1.13 and you divide it by 100, because that's what percent means, it means out of 100, then you'll get the correct decimal form of the percent. Divide it by 100, and this is what we have. Alright, so we got our rate written as a decimal form of percent. Now, do we know the time? Well, in part B, we're going to be given some times, but let's write our function so far as we know it first. We've got A of t equals P. Oops, we know what P it is. We know that P is 6.8. And we're going to need to remember that this is in billions, but we'll just write 6.8 here. Times e to the, we have k, 0.0113 times t. We don't know t yet until we do our first problem. So this is our answer to letter A. We've found the exponential growth function for this population. In letter B, we're actually going to use it now. So in B, we want to find the population in 2012 and in 2020. So we need a t, we need a time. Well, let's think about this. The initial population is from 2009, so the time that's passed is 2012 minus 2009. So this is 3 years later. Alright, and when we do 2020, what's that? That's going to be 11 years later. So those are the two t values that we're going to use in the equation. So if I want to start with A of 3 years later, that's 2012, I'll do 6.8 times e to the 0.0113. Be careful with those. Times 3 years. We know our t now. And then this is just plug and chug, because everything on this side of the equation is a number, including e. That's not a variable, that is a number. So it's all can be calculated. So 6.8 times, punch your e, your exponential key, e to the 0.0113 times 3. Close your parentheses, and I get about 7.03, let's go with 4. 7.034. Now remember, this was in billions. So our population will be about 7.03447, etc. billion people. So always label your answers. Alright, now let's do the second part of B. We need to find the population in 2020. And so that's 11 years after 2009, so I'm going to be doing A of 11. Same deal as we did last time, putting the 11 where t is. So e to the 0.0113 times 11 this time. Now if you're lucky enough to have a calculator that has the function still in it and you can get to the function, I can arrow back over to it and I can replace this 3 with an 11 and close my parentheses, and I get a population of about 7.7 billion people. So it doesn't seem to be growing too terribly fast. We go from 6.8 billion in 2009 to about 7 billion in 2012. I wonder if that was accurate, by the way. We could look up the stats for 2012 and see. And then we get about 7.7 billion in 2020. Now we have one thing left to do, and I'm going to go to another piece of paper because I'm not going to have enough room here. We have part C. Now part C asks us to find out when will the population be 8 billion. Now this is asking when will the result be 8 billion. This is a result question. So in this case, we don't know the when. We don't know t, and we are trying to find, we know a of t. We know that 8 billion is a of t. So if we look at the function now, let's recopy it. A of t equals p times e to the kt. This time we know a of t. We know the result. It's 8 billion. Okay? And what we don't know is the when. We don't know the t. So this gets a little bit trickier to solve. We still know the rate. It's still growing at this 0.0113 rate, but we don't know t. Alright, in this case what's going on is we also know p, so I can rewrite it one more time with our initial population is still 6.8, still what our model is based on. So there. Now I've got the function to the point where I know everything except the time, the when in my question. How do we solve these? Now you did get some practice with solving exponential equations. Remember what we do? We get the base alone, and then we're going to put it in logarithmic form. So we got to get this base alone first. So in order to get the base alone, we got to get rid of the 6.8. How do we do that? Well, since it's being multiplied by e, I need to divide both sides by 6.8. So I do 8 divided by 6.8, and I get about 1.176. I'll leave that in my calculator. Okay? Now, because the the variable is buried in the exponent, I can't solve this unless I put it in logarithmic form. Now, in this case, because it's e, I'm going to put it in ln form. I'm going to take the ln of both sides. So here's what I do. If I take the ln of e, these two things, as you know, they share the same key on most of your calculators. They share the same key on my calculator. So if I take the ln of e, it's going to undo e. What I do on the other side is the same thing. I have to take the ln of 1.176. What I do to one side, I do to the other. So taking the ln of e, ln cancels out e, their inverse operation. And what comes out is this 0.0113 times t. It's like the exponent crashes to the ground now because ln ate e. And on the other side, I can actually calculate this because ln is a key on my calculator. So I press my ln key, and mine is right near my log key, right there. And it brings up a pair of parentheses, and I put in the 1.176. And I press enter, and I get about 0.162. Now I just have a linear equation to solve. I need to get t alone. So I'm going to divide both sides by what's stuck on t. That's the 0.0113. Forget that 0 after the decimal point. You know, I already have that last answer in my calculator, so I can go divided by 0.0113, and I end up getting about 14.3. So t is about 14.3. Well, what the heck does that mean? Well, it means in about 14.3 years, the population of the world should reach about 8 billion. Remember what the question was. I always go back to your question. When will the world population be about 8 billion? In about 14.3 years. And there's my answer. Always make a conclusion to your answer. Go back, read the question again, and make sure you have an answer that makes sense.